what we have described up to now is the concept of hydrophilicity. Hydrophilic, meaning water-loving. And the idea of water-loving, because of the dipole moments on water and because of the charged nature of ions, hydrophilicity comes down to the idea of charge. It comes down to the idea of charge interactions between a molecule, an ion, and the dipole moment on water. So over here, we're going to describe over here the idea of hydrophilic. Again, coming out of the Greek, meaning water. Philic, meaning loving. And those things which are hydrophilic are charged, such as ions, and we'll see a little later called polar, such as alcohols. Those things which are hydrophilic want to interact with water. They want to use the charge or the polar nature of the molecule to basically interact. This interaction of charge with the dipole moment of water. This is telling us we've got to have a charge for hydrophilic molecules. The other character I'm going to put clear over here is its exact opposite, is hydrophobic. Hydrophobic, again, means water. Phobia comes from the Greek, meaning fearing. These are water-fearing. Where these are easily soluble in water. These are insoluble in water. The hallmark of these hydrophobic molecules is that they tend to be uncharged. This uncharged nature derives from equally distributed electrons. This is especially true when we talk about triglycerides. Triglycerides are in fact fats. Whether they're animal fats or if they're vegetable oils, such as canola oil, olive oil, or peanut oil. There's again meaning in the terminology here, tri meaning three. Glyceride derived from glycerol. Glycerol, I'll put this together here. Glycerol is a 3-carbon alcohol. Whenever you see this term alcohol, think OH. We'll have 3 carbons, 1, 2, and 3. You'll remember from basic chemistry that each of these carbons needs to have 4 bonds, needs 4 covalent bonds. The 4th bond here is to an oxygen, which is then to a hydrogen. Again, when you see the term OH, you think alcohol. This is a 3-carbon alcohol. 1, 2, 3 carbons, 3 OHs. It's a 3-carbon alcohol. Glycerol is the foundational or backbone molecule of all triglycerides. So what we'll see, and I'll generate this molecule first by connecting this molecule to something known as a fatty acid. Here we have a carbon, a double bonded oxygen, and an OH. And then this great long chain of carbons. Now I won't go and write all of these out, but these carbons, the carbon chains and fatty acids in biology tend to be 16, 18, 20, some of them as long as 22 carbons. I won't go through all of that. But there's this great long string of carbons. I'm going to tell you that all of these carbons have a hydrogen attached to it. This will be a saturated fatty acid. Now, sometimes what we'll see is that there are these carbons that are double bonded. And this is an unsaturated bond. Or an unsaturated, I should say, fatty acid. Many of the vegetable oils have a single one of these unsaturated bonds. I'm not going to get too much into that. But what I want to show you is that we can have these carbon double bonded OH. And this is called, whenever you see a carbon double bonded oxygen OH, this is something known as a carboxylic acid. This is a fatty acid because at one end of the molecule there's this carboxylic acid and this great long string of carbons. What we can do with some magic and mostly some enzymes is we can take this hydrogen and this hydroxyl. We can now remove the hydrogen and the hydroxyl as water. And now we're going to produce a carbon-oxygen-carbon bond. When this carbon-oxygen-carbon bond, when this carbon has a double bonded oxygen on it, this is said to be an ester bond. And we can do this for each of the fatty acids. So that now we have 3 ester bonds linking the oxygen of the glycerol with these long fatty acid side chains. The fatty acid side chains have all of their electrons equally distributed, so these fatty acid side chains are uncharged. All 3 of these fatty acid side chains are uncharged, so that if you try to put this molecule into water, because it's uncharged, it won't go into solution. It is hydrophobic. Go home and make a salad and do this. Take some olive oil, put it in a carafe, add water, and you know what's going to happen. It's going to float to the top. You can shake it and shake it and shake it, and you can put it into these tiny little droplets of olive oil, but give it 20 minutes, and it's going to settle out on the surface again because the olive oil is less dense than the water, and they won't go into solution. So that's the idea of hydrophobicity and triglycerides. We'll come back to this tomorrow and incorporate that into phospholipids.